Okay, let's go on to something completely different. My name is Heiko Gerstung. I'm managing director of a small little company called Meinberg coming from Germany. And we are experts in providing time synchronization to all kinds of different application spaces, from defense to hyperscalers to telecom, power grids, you name it. And I'm going to talk a little bit about hardening GNSS time today, trying to raise some awareness of the topic in various events. So the subtitle says a method to counter spoofing attacks. Obviously there are more than one method, so when I chose that subtitle I was already implementing the first mistake in my presentation. Apologies for that. Those of you who attended Jill's presentation earlier today already heard about GNSS being used as a source of time. So in general, timing is one of the hidden, basically, infrastructures behind a lot of applications. You would be very surprised where timing is required in order to keep our modern world humming along. And GNSS is used not only to help you to find your way to the hotel and to this Congress Center or home sometimes. It's also used to provide timing to a lot of different critical infrastructures on this planet. One of the reasons for that is that it's free. It's available globally, so we have customers using the signals of these satellites in the Antarctic Sea, in the Sahara Desert, and basically on every spot of this planet. That's one of the main reasons. It's super accurate. The performance of GNSS is very good. And so when it's free, it's available everywhere, and the performance is great. That's a number of good reasons to use it for timing. But GNSS has been used as the name GPS basically tells you to find your position on the planet, and that's done by comparing the time of arrival of the signals from multiple satellites, and because your receiver knows the position of these satellites in space, because they tell it to the receiver, they can calculate where exactly they are in a three-dimensional space. And this is only possible on the let's say performance level that we see. We are talking about meter level positioning these days, because the satellites have highly accurate clocks on board flying with them through space, and these clocks are steered from the ground stations to stay aligned to global time. GNSS is used to provide stability to the power grids, which I always call the most critical infrastructure of all. If your power grid falls down, yes, you have UPSs and yes, you have generators, but not everyone has those. And after a few, let's say, minutes, the first system probably start to get into trouble, and after a day, it will be very hard. After a week, we are probably not back to the medieval age, but a lot of things will not work as we all are used to see them working. So that's why it's probably the most critical application of all, followed closely by the telecommunication networks, because those are used to connect everything together and in order to make every system aware of the status of the other one, for example. Yeah, a lot of others, financial data centers, broadcasting media networks. When in Germany football is basically shown on the TV, and there is an interruption of that service, that is considered a national crisis, right? So you will see riots, you will see, no, I'm just joking, but media and broadcast is also considered a critical infrastructure. not talking about defense applications where people are relying on systems to work. Yeah, very, very important. So GNSS is used everywhere, but it is also a vulnerable system. First of all, the signals are very weak. Jill talked about that also earlier this morning. GPS satellites are flying through space around 22,000 kilometers away from Earth. They are power constrained. You cannot plug a cable into a satellite to power it with endless power, so they are relying on a stringent power budget. So the signals that are transmitted by the satellites are pretty weak in comparison to everything else we know in terms of wireless communication down here on Earth. They are typically, the satellite signals are typically found in the noise of the radio signals. And jamming, which means transmitting a radio signal that overpowers the original GNSS signals, is pretty easy. You can use a battery-powered device or something that you can plug into the 12-volt DC port of your car, and you can basically wipe out the GNSS signal in multiple kilometer wide range if you want to do that. So it's very vulnerable from that end. The non-military GNSS signals, so those that are free to use and that you can use in your applications, are unprotected. So when we talk about network protocols, think of Telnet or HTTP. Everything is unencrypted, and there's no mechanism built in which allows to authenticate the signal in the receiver. So anybody could basically generate a signal that looks like a real GPS signal, and a receiver is typically not capable of telling the difference. There are some methods to do that, but in general, it is an unprotected, unencrypted signal that can be generated by anyone. So the estimated time of arrival is the key. That's the main basically mechanism used for positioning. So what you can also do is you can delay a signal. So in case you don't want to manipulate it, but you still want to attack a GNSS-based application, you could receive those original signals with your own receiver and record them and play them back after a short while, which will delay the signals, and you basically retransmit them, but with a short pause in between, and that will mess up the timing of the target. Since the signals are, as I said earlier, not super strong, you don't need a big transmitter. You don't need a truck or anything to target a specific antenna somewhere. So jamming, going a little bit deeper into the different attack scenarios here, or attack vectors. It's a denial of service attack. So basically you wipe out the signal, and everyone in the coverage area of your transmitter is not capable of using GPS anymore. There have been multiple examples where this happened. One of the last ones was in Denver, Colorado, I think last year, at the airport, but we know a number of examples. Truck drivers sometimes use jamming devices because they have a GPS tracker or a GPS receiver in their car, so that their boss knows exactly where they are and that they are not visiting their girlfriend when they are supposed to be working. So in order to trick these trackers, you can buy GPS jamming devices and plug them into the car's DC power socket, and then it will wipe out the signal. If you have a high quality jammer, it will only do that in a very small circle, so let's say 5 meters or something. But if you have something that is not behaving correctly, it could wipe out the signal in a kilometer or something like that. And there have been examples where a guy had this jammer in his car, drove to the airport and flew off to a 2-week vacation and didn't think of turning it off. And then when he came back, he did not find his car because police had to basically open it, disconnect the jammer, and of course send him a nice invoice for all the costs that have been generated for the airport to close down operations for a while. The technology or the strategy to fight jamming or to protect against jamming is what we call holdover. So one of my claims is that holdover is your friend. That basically means you have a stable clock in your system that is disciplined using the GPS signal while it's available. When the GPS signal goes away due to jamming or due to some failure of your antenna or some unintended disruption, it will continue to provide timing to the application, but then it will go to this stable clock that you built in. And depending on the stability of this clock, you can survive an outage of the signal for a certain amount of time. That's a function of how accurate do you need to be, how accurate does your application need to be, and how much time do you want to bridge to such an outage, for example. So there's all kinds of different solutions on the market, from a $5 OCXO to a $100,000 cesium clock, for example. So meaconing is, as I said, attacking the signals. You don't need to regenerate the signals, which imposes a certain, let's say, technical challenge. So meaconing is a lot easier. The only thing you can do against that, because you are basically receiving the original signals, is you try to detect it, and then you turn off you don't use the receiver's signals anymore. Basically, it turns into a jamming attack, it turns into a denial of service attack as soon as you can detect that you are attacked using a meaconing attack, and then you just stop using GPS until it's over and you go into holdover. It's hard to detect, the signals remain unchanged, and the only chance here is to look at the signal characteristics, for example, the field strength of the received signal, which is typically a lot higher than the original signals. If you have very clever antennas, these antennas and receivers can detect from which direction they receive a certain signal. And with a meaconing attack, all your signals are coming from one direction, because the retransmitter is overpowering the original signals, and that also is a 100% confirmation that you are subject to a meaconing attack. But not every receiver has these capabilities. So spoofing is actually like a man-in-the-middle attack, which means that someone is sending you manipulated GPS signals or GNSS signals in general. It's not super easy to carry out because you have to really generate the signals from scratch. And in the past, it was super hard. You had to buy a nice Spirent GPS simulator for $50,000 or something. These days, you can download some open source software and use a HackRF SDR, basically a software-defined radio, and you will be probably set back $300, and that allows you to generate GPS signals from scratch. And then you can change the timing in these signals or change some positioning parameters, and that will trick the receivers into believing they are somewhere else or they are at a different time. It's also very hard to detect. The signal content integrity is one good thing to look at, but that typically requires additional data because, as I said earlier, the signals are unprotected. There's not even a hash or anything, and there are hashes, but they are easy to recalculate. So when you are generating a signal, you just calculate the right hash and send it together with the signal. You can also, just like with a meaconing attack, see that, look at the signal characteristics, what is the power of the signal you're receiving, and do you receive everything from one direction? Military antennas, there are military antennas in the market which have 7 segments, so they can basically find out that there are stronger signals than usual from 7 different directions, and can blank out or ignore up to 3 of them. So that would allow a tank, for example, to ignore the spoofed signals when these signals are coming from 3 different directions. The cost of one of these antennas is $25,000, $30,000 US dollars. So typically not the thing that you put on a data center, if you're able to get it. So how can we detect spoofing attacks? Some signal content integrity data is available. Galileo introduced, or they are in the process of introducing, a service called OSNMA, so that's the Open Service Navigation Message Authentication Service. That will provide some symmetric keys, and it will reveal the keys a few, let's say, moments after the signal has been sent. So it's like a Tesla approach where you get keys, you get a digitally signed signal, and then you will get the keys to verify that this digital signature is valid a few minutes or sometimes seconds after the fact. There's also a commercial service available, which is called Atomicron, from a company called Fugro. This service uses around 100 reference stations distributed all over the world. These reference stations receive the original signals from all the 4 constellations, all the 4 major constellations, and all the satellites, and then these signals are transmitted to 2 data centers. For redundancy reasons, they have 2 data centers. And at these data centers, you have basically a complete picture of every single satellite, of every one of the 4 constellations of the whole Earth. And then they are calculating something like a hash that is transmitted to each Fugro or Atomicron capable receiver with their own, let's say, geostationary satellite. It's not their own satellite, but their own channel. So they are using geostationary satellites. So a Fugro Atomicron capable receiver will receive the original GNSS signals, and it will also receive this additional signal from the geostationary satellite, and that will allow him to verify that the GNSS signals it just received a few seconds ago are okay and are basically untampered and unmanipulated. So and since the geostationary satellites, there are 7 of them around, basically covering almost every part of the Earth except the pole regions. This is also a globally available service, which only requires basically the power for the receiver. You don't need any additional infrastructure, so it's available everywhere where you have free view to the sky and can put an antenna on the roof. Short comparison, we have the Galileo OSNMA. It's free to use. It only protects the E1 transmissions from Galileo satellites, so no GPS, no Beidou, no GLONASS. And the Atomicron service protects all the 4 major constellations on all the frequencies, for example, GPS L1, L2, L5. But it is a subscription-based commercial service, sets you back around 100 euros per month per receiver. And then you are, of course, also capable of choosing a GPS receiver or GNSS receiver that allows you to detect these attacks based on the signal itself. Okay, so just to summarize, we have holdover and we have source diversification as common protection methods. You take a stable clock in your system, and you also use different sources to make sure that you can compare those. And the call to action here is that we need to define attack scenarios and methods to defend timing applications. So I ask you to participate in the OCP tab working group where we are discussing these things. You will find a lot of experts there, and they want to hear from the application side, from the users, to make sure that they can prioritize the different methods of protecting the signal or the applications in the right order. Okay, thank you.